Welcome. Today we're diving into the fascinating world of assembly language in computers. Assembly language acts as a bridge between human-readable code and the binary instructions that computers actually execute. It's a crucial topic for anyone interested in how computers really work under the hood. In this video, we'll explore what assembly language is, why it's important, and how it fits into the bigger picture of programming and computer architecture. Let's start by understanding the basics and setting the stage for a deeper exploration of this foundational technology. Assembly language is a low-level programming language that's closely tied to computers' hardware. Unlike high-level languages like Python or Java, assembly language provides instructions that correspond almost directly to machine code, the binary code that a computer's processor understands. Each assembly instruction typically represents a single operation, such as moving data, performing arithmetic, or controlling program flow. This makes assembly language both powerful and challenging, as it requires a deep understanding of the computer's architecture. You might wonder why anyone would use assembly language when higher-level languages are so much easier to write and understand. The answer lies in control and efficiency. Assembly language allows programmers to write code that runs extremely fast and uses minimal resources. It's often used in situations where performance is critical, such as embedded systems, device drivers, and real-time applications. By working directly with hardware, programmers can optimize every instruction, squeezing out the best possible performance. Assembly language is often described as a human-readable version of machine code. While machine code consists of binary numbers, assembly uses mnemonics, short, easy-to-remember words like MOV, ADD, or JMP to represent instructions. These mnemonics make it easier for humans to write and understand programs, but they still map directly to the binary instructions executed by the processor. This close relationship is what makes assembly language so powerful for low-level programming. To turn assembly language into something a computer can execute, we need a special program called an assembler. The assembler takes the human-readable assembly code and translates it into machine code, which is made up of binary instructions. This process is essential, as computers can only understand and execute binary code. Assemblers also help catch errors and can provide helpful feedback to programmers, making the development process smoother. Assembly language consists of a set of basic instructions that perform simple operations. Common instructions include MOV for moving data, ADD for addition, sub for subtraction, and JMP for jumping to another part of the program. Each instruction is designed to perform a specific task, and by combining them, programmers can create complex programs. Understanding these basic instructions is the first step to mastering assembly language. Registers are small, fast storage locations inside the CPU that assembly language uses to hold data temporarily. Each processor has a set of registers, such as AX, BX, CX, and DX in x86 architecture. These registers are used for arithmetic operations, data movement, and controlling program flow. Efficient use of registers is key to writing fast and effective assembly programs, as accessing registers is much quicker than accessing memory. Assembly language, accessing memory is a fundamental operation. Instructions like MOV can transfer data between registers and memory locations. Understanding how memory is organized and addressed is crucial for effective assembly programming. Programmers must manage memory carefully, as mistakes can lead to bugs or crashes. This level of control is both powerful and demanding, requiring attention to detail and a solid grasp of computer architecture. Assembly language provides instructions for basic arithmetic operations, such as addition, subtraction, multiplication, and division. These operations are performed directly on registers or memory locations. For example, the ADD instruction adds two values and stores the result in a register. Mastering these operations is essential for writing programs that perform calculations or manipulate data at a low level. Control flow instructions in assembly language determine the order in which instructions are executed. Common control flow instructions include JMP for unconditional jumps, and conditional jumps like JE, jump if equal, or JNE, jump if not equal. These instructions allow programmers to create loops, branches, and decision-making structures, forming the backbone of complex programs. Labels and comments are essential tools in assembly programming. Labels act as markers in the code, making it easier to jump to specific locations. Comments, on the other hand, help explain what the code is doing, making it more readable for humans. While labels are used by the assembler, comments are ignored during execution but are invaluable for documentation and maintenance. Syntax of assembly language varies depending on the processor architecture and assembler being used. However, most assembly languages follow a similar structure, an instruction mnemonic, followed by operands such as registers or memory addresses. Understanding the specific syntax rules for your target architecture is crucial for writing correct and efficient assembly code. Assembler directives are special instructions that tell the assembler how to process the code. They don't generate machine code themselves but control aspects like memory allocation, code organization, and symbol definitions. Examples include directives for defining data segments or specifying the starting point of a program. Mastering directives helps programmers structure their code more effectively. Macros are a powerful feature in many assembly languages. They allow programmers to define reusable code blocks that can be inserted into the program wherever needed. Macros help reduce repetition and make code easier to maintain. When the assembler processes the code, it replaces each macro with the corresponding set of instructions, streamlining development. Interrupts are signals that temporarily halt the normal flow of a program to handle special events, such as hardware requests or errors. In assembly language, handling interrupts involves writing special routines called interrupt handlers. These routines respond to specific events and then return control to the main program. Understanding interrupts is crucial for writing responsive and robust low-level code. Stack is a special area of memory used for temporary storage in assembly programs. Instructions like push and pop add or remove data from the stack. The stack is essential for managing function calls, local variables, and return addresses. Proper stack management is vital for program stability and security, as stack errors can lead to crashes or vulnerabilities. In assembly language, function calls are managed manually using the stack and specific instructions. Programmers push arguments onto the stack, call the function, and then clean up the stack afterward. This process gives programmers full control over how functions are called and how data is passed, but it also requires careful attention to detail to avoid errors. Assembly language programs interact with the outside world through input and output operations. These operations are often performed using special instructions or by calling routines provided by the operating system. Handling input and output at the assembly level requires a good understanding of the hardware and system software, making it a challenging but rewarding aspect of low-level programming. Debugging assembly language code can be challenging due to its low-level nature. Programmers often use specialized tools like debuggers and emulators to step through code, inspect registers, and monitor memory. Careful debugging is essential for finding and fixing errors, as even small mistakes can have significant consequences in assembly programming. Assembly language is widely used in embedded systems, where resources are limited and performance is critical. Writing code in assembly allows developers to optimize for speed and memory usage, making it ideal for devices like microcontrollers, sensors, and other hardware with strict constraints. Mastery of assembly is a valuable skill for embedded systems engineers. Device drivers are programs that allow the operating system to communicate with hardware devices. Many device drivers are written in assembly language to achieve maximum performance and direct hardware control. Writing drivers in assembly requires a deep understanding of both the hardware and the operating system, making it a specialized but important area of programming. Real-time applications such as robotics and industrial control systems often rely on assembly language for their critical timing requirements. Assembly allows programmers to write highly efficient code that meets strict deadlines, ensuring that the system responds quickly to inputs and events. This makes assembly indispensable in fields where timing and reliability are paramount. Learning assembly language can be challenging, especially for those used to high-level languages. It requires a solid understanding of computer architecture, memory management, and low-level operations. However, mastering assembly provides valuable insights into how computers work and can make you a better programmer overall. Assembly language plays a significant role in computer security. Security researchers and hackers often use assembly to analyze malware, reverse engineer software, and find vulnerabilities. Understanding assembly is essential for anyone interested in cybersecurity, as it allows you to see exactly how programs operate at the lowest level. Reverse engineering involves analyzing a program's assembly code to understand how it works, often without access to the original source code. This process is used in software analysis, security research, and even software compatibility efforts. Mastery of assembly language is a key skill for reverse engineers, as it allows them to dissect and understand complex programs. Operating systems are often written, at least in part, using assembly language. This allows developers to implement critical functions like bootloaders, interrupt handlers, and context-switching routines with maximum efficiency. Understanding assembly is essential for anyone interested in operating system development or low-level programming. Compilers for high-level languages often generate assembly code as an intermediate step before producing machine code. This process allows for optimization and fine-tuning of the final executable. Understanding how compilers translate code into assembly can help programmers write more efficient high-level code and debug complex issues. Assembly language is specific to each processor architecture, such as x86, ARM, or MIPS. This means that assembly code written for one type of processor won't work on another without modification. Understanding the differences between architectures is important for writing portable and efficient assembly programs. Performance tuning is one of the main reasons to use assembly language. By writing critical sections of code in assembly, programmers can optimize for speed, memory usage, and power consumption. This is especially important in applications where every millisecond counts, such as gaming, scientific computing, and mobile devices. While assembly language offers unmatched control and efficiency, it also has significant limitations. Programs written in assembly are harder to write, debug, and maintain compared to high-level languages. They are also less portable, as code must be rewritten for different processor architectures. These challenges mean that assembly is best reserved for situations where its benefits outweigh its drawbacks. High-level languages like Python and C are much easier to use than assembly, offering features like abstraction, error checking, and portability. However, they sacrifice some control and efficiency. Assembly language, on the other hand, provides direct access to hardware but requires more effort and expertise. Choosing the right language depends on the specific needs of your project. Despite the rise of high-level languages, assembly language remains relevant in modern computing. It's used in system programming, embedded development, and performance-critical applications. Understanding assembly gives programmers a deeper appreciation of how software interacts with hardware, making it a valuable skill even today. There are several popular assembly languages, each tailored to a specific processor architecture. Examples include x86 assembly for Intel and AMD processors, ARM assembly for mobile devices, and MIPS assembly for embedded systems. Learning the assembly language for your target platform is essential for effective low-level programming. A variety of tools are available for assembly programming, including assemblers, debuggers, and emulators. Popular assemblers include NASM, MASM, and GAS. These tools help programmers write, test, and debug assembly code, making the development process more manageable and efficient. There are many resources available for learning assembly language, including books, online tutorials, and community forums. These resources can help beginners get started and provide advanced tips for experienced programmers. Taking advantage of these resources is key to mastering assembly language. Writing your first assembly program can be a rewarding experience. Start with simple tasks such as moving data between registers or performing basic arithmetic. As you gain confidence, you can tackle more complex projects such as implementing loops or handling input and output. Practice is the key to becoming proficient in assembly language. Common mistakes in assembly programming include incorrect use of registers, improper memory access, and stack mismanagement. These errors can lead to crashes or unexpected behavior. Careful attention to detail and thorough testing are essential for avoiding these pitfalls and writing reliable assembly code. Following best practices is crucial in assembly programming. This includes writing clear and well-documented code, using meaningful labels, and organizing code logically. Regularly testing and debugging your code helps catch errors early and ensures your programs run smoothly and efficiently. Modern CPUs are highly complex, with features like pipelining, caching, and parallel execution. Writing efficient assembly code for these processors requires an understanding of these features and how they affect performance. Advanced programmers can leverage these capabilities to write highly optimized code. Assembly language is often taught in computer science courses to help students understand how computers work at a low level. Learning assembly provides valuable insights into computer architecture, operating systems, and the inner workings of software. It's a foundational skill for anyone pursuing a career in computer science or engineering. While high-level languages continue to evolve, assembly language remains relevant for specialized applications. As technology advances, new processor architectures and devices will continue to require low-level programming expertise. Assembly language will always have a place in the world of computing, especially where performance and control are paramount. Let's recap what we've learned about assembly language. We explored its role as a bridge between human-readable code and machine code, its importance in performance-critical applications, and the challenges and rewards of low-level programming. Assembly language remains a vital tool for understanding and controlling computers at the most fundamental level. If you're interested in learning more about assembly language, consider exploring additional resources, experimenting with code, and joining online communities. The journey to mastering assembly is challenging but incredibly rewarding, offering insights that will benefit your programming skills for years to come. Assembly language is used in a wide range of practical applications, from embedded systems and device drivers to security research and performance tuning. Its unique combination of power and precision makes it indispensable in many fields. Understanding assembly opens up new possibilities for innovation and problem solving. Thank you for joining this journey into assembly language. We've uncovered how it works, why it matters, and where it's used. Whether you're a beginner or an experienced programmer, understanding assembly language will deepen your appreciation for computers and enhance your programming abilities. Keep exploring, keep learning, and embrace the power of low-level programming.